Leah, you're looking really well today. Like more elegant.
I know.
Was that on purpose?
No, I use like oil for the.
I cut my own hair today.
I don't have this kind of problem.
Yeah, some mornings.
Yeah.
Yeah, I put oil on it. You can see it too.
Okay, let's make a start. Welcome to Neuroccino, everyone. There will be people dropping in later on, I think, today. It's the 15th of March today, 9:30, and we have, I think, one book presentation and two papers, if everyone is coming into the chat from the background. Let's make a start. Leah, do you want to start with the book for today?
Okay, so I share the link in the chat box if you want to. Now I'm gonna share the screen here. Okay, if I jump from a page to another, you can see it, right? Okay, because let's go to the beginning. So the book I'm gonna talk about is Think Bayes by Alan Doney, and I want to show you briefly that I started reading the first edition. That this is the cover, and it's a really nice book because it's really readable. I don't know if you get, so it's easy to read and follow, but you also can find there Python codes for then implement what you learn from a theoretical, from a theory point of view. And it's really nice that this is the first edition, and now there was this second one. Also, the first edition is all HTML, so you can find it online. But in this second edition, I found the Python code updated and really easy to follow. Like you have, you use, for example, a data frame for the Panda libraries. You have NumPy, so other statistical libraries, for example, for the Monte Carlo implementation. And so you can find all the example here through the books that I will show you in a bit. And also you have the Jupyter version of the book, so you can run directly the code online without install everything on your laptop if you are interested. In my case, I tried to install everything on my computer to see if then I was able to run all the analysis or something was missing. And so here you can see all the chapter of the book, and starting from the beginning is uploading. Wait, should be okay. You have all the here, as I was saying, you have all the Python examples. Then you can copy and paste on your computer. And I found it really interesting the use of data frame, where you can define the rows called index in the data frame. So everything is labeled, and you can call that. So, or each feature, like using the columns indexes, or also the row using the index option in the data frame. And then you can merge the for example, different probabilities by multiply the different data frame, and you can manipulate these objects, and it's really useful and also intuitive to use, because you can really see everything how is structured. But going back to the beginning, so here in this chapter, you have examples of how the data frame can be used for probability. and it's really useful. I think I don't have the time to go through all the examples, but yeah, here you have like everything. And starting from the first step, so what's the biggest theorem? There are different declinations, so different ways that you can talk about this the theorem. I like this one, where you have the hypothesis, so the hypothesis that you want to test, and the information from the data. So in the Bayesian theorem, the probability that your hypothesis is true based on the information that you have from the data is the probability of your hypothesis, the probability that the data given the hypothesis, and it's called likelihood, and divided by the probability that the existence of your data. So some more words that are typical of the Bayesian statistics is this one. So it's the likelihood, and the what you obtain after is the posterior probability. And everything, like if you want to assess the probability, for example, of this hypothesis is true given the data, is look into the posterior probability. So one of the main differences between here than we will see, for example, in when you have testing compared to typical t-test statistics, is that we don't there are not p-values, but distribution of probability. In this case, we look to the posterior probability, that is the product of all these contributions, to look how much is probable that our hypothesis is true. And everything starts from the data. So this is important. Another word, another typical term that we use is the prior distribution, is that the probability of your hypothesis is true without knowing nothing. So as we want to say how much an event is probable without knowing the data. So something intrinsic to your hypothesis. Sometimes could be like a uniform probability. So there's not like a preferential event, or can be a Gaussian probability. So if you have like the knowledge of data from the past, you see that it's more a Gaussian distribution that moves near a mean value. And so I like this view of the Bayesian theorem, because it really gives you the idea that everything is based on the data. And so yeah, there should not be like assumptions or models, but just look to probability. But however, sometimes you have to do some assumption, for example, about the prior distribution. So then in the next chapter you see other examples how to use distributions. For example, a useful instrument is the probability mass function, where instead of just have a sequence of events, you put them all together. And so from the table, you can go to the distributions. And for example, here, if you have the word Mississippi, using this function, you have the probability that each letter is in the word. And so in this case, the S and the E are the most probable, as you see. And so here there are really simple examples that make you start like think Bayesian. So have this view. For example, one of the examples that I really liked is the cookie problem. The cookie problem. So you have two balls, and you have information at the beginning where this is like the number of the cookies that each balls have, and the number of chocolate cookies that there are inside. And you have, for example, to assess the probability that you will extract a vanilla cookie or a chocolate cookie based on these information. So really simple examples, but then can be translated to like a lot of scientific data frame. These are really simple to start to use this function. And one thing that is important is that every time that you have information from the data, so which is inside the likelihood, as we have seen, you have to update your posterior distribution. So there is always this this process. So the data gives you some information. You have to update the posterior distribution, so the probability of a hypothesis. Or if you like, then pick another cookies and you want to assess the probability again of a vanilla cookie, you have to update your distribution. And this is something that is really intrinsic in the Bayesian book. Of course, you will have also like in the book are described some distribution as the binomial distribution or the Poisson distribution, and these are typical of like statistical background that are used here. And so here there are a lot of examples. I don't know if I have the time to go through all the examples. So for example, here you are waiting at the station and there is like, it's a moment where all the people are there, for example, like for 5 p.m. and you have to assess if it's more it is better to wait for the next train or take a taxi. And there are all the informations about your knowledge, so the time where each train arrived, and all this information, and you put all of these, and you try to describe these in Python codes, and then defining functions and trying to update the posterior distributions, so your probability mass function. And here you can find all the examples if you are interested. Another useful representation of the Bayesian framework are the odds. So you have the ratio between the probability of your event and that will happen, and the probability if your event is not happening. So 1 minus the probability of your event. And then the odds is a representation of this ratio, and you will have like a real number. So for example, the odds of 0.75 will be 3. So 3 to 1, you can also find something like that, written something like that. It's really used like, I think in football matches or single competitions. So it's something that we are used to hear. But for example, the odds against, the odds in favor. But here there is all the, so there are simple functions, but they're really useful to have. Another interpretation of the Bayesian theorem is the Bayesian rule, where you describe the theory that we have seen before using the odds. So in these cases, the odds of your event A is will happen given the data will be the odds of the event A and the ratio of the likelihood distributions of the data given the hypothesis A, or the data given an alternative hypothesis, in this case B. So here we don't have the posterior distributions, but we have the odds in favor and the product with the likelihood ratio. So it's another way to find the to assess the probability of your hypothesis against an alternative hypothesis. And this one is the famous Bayes factor, which is can be seen as the ratio of the odds and or the Asian of the likelihood. And this is what we found usually in, for example, in publications right now, or where we assess yes, the probability of if an hypothesis is true against another. And here again, all the examples. It's really nice because, for example, you can try to compute these and then click show, and you have the results. And again, so it's really nice to follow. And also there are a lot of examples. Yes, there are many. I have no time to go through everyone. But and then you have always a summary. That is really like the take-home method, and so it's really like when you are like you going on all the details before, and then you have what it's needed to go to the next chapter, and also it's nice because sometimes at the beginning of the chapter they say if you are not interested in this or this, you can skip to the other chapter. So it's not like that you have to know everything. It's really like to guide you to understand and then implement what you are interested to. And then you can also do the exercises. And again, it's nice because you don't have the solution, but then if you click, you have the solution. So it's not like it's really nice also this part. And then going through, for example, here in the decision analysis, I really like it because sometimes you were wondering like how we construct these prior distributions. How can I have this from my data, or how can I construct the likelihood? And here there is this, I think it's like an American television game show where they have to guess the price of something, for example, a car or a computer. They have the range of an error that they can make, and it's nice because here I understand that really everything is from the data. So here they look to all the information, like in all the editions, how where were the guess, where were the errors, and based on that they assess the probability that you will do some errors or a right guess. So here I really understood that if you suppose that everything is from the data, so also your prior distributions, you have all the showcases in the past, the bit, the difference given. Then you have also the ground truth, so you know what was the right answer, and based of all the errors that were made in the past or the guesses, you will assess their error, the probability that your guess will be right in the edition. And so this is really useful, I think. Then here in testing, you for example, you will find here there is another example where there is this coin that is a little bit strange, because every time it gives you like an ad 150 times in case 110, and you have to understand if the coin is biased or not. So here you don't look to each single event, but a statistics of all the events, and you try to understand if the coin is biased or not, looking to the probability. So if there is a certain probability that this event is true or not. And yes, here again you look to the Bayesian factor, also called K. There are like, usually in the Bayesian statistics you have like different ways to express or write the same things, but it's always like the same, I would say. And what else in the comparison? what? In the comparison, you look not just to like one variable, but you start to look at the two variables at the same time. So, for example, here you have to assess the how much a person is tall given the height of another person, and you have like a relationship between the two. And classification, you have again the famous penguin data set that is used like in a lot of examples. So given some features of the penguins, you have to try to classify new penguins in the right species. And here it's you will try to do this using the Bayesian statistics and so distributions. So again, look into the posterior distribution and how much is probable. And here in the inference, yes, so here there is the alternative of the t-test that you can find here. So you will so you not look to p-values, but you look to the distributions of the difference of the difference of two events. So this new way of represent the posterior distribution, and again you will find all the, maybe it's boring, I'm going through all the details, but yeah, here you will find all these all the examples. For example, here to differentiate a control group with a treated one. And then in the survivor and mark and capture, you have other examples looking to like where you have more variables. And then the logistic regression I really liked because you have a way to describe, like you have this sequence of probability that I have also some notes that it's like a geometrical sequence, and it's really nice because it's like it's explained based on something that appeared, I think, in real, I don't know. So when the author is going to a class that it was supposed to be like a computational class, so usually they were like only males, and he arrived in this class and it was like the first, and there was like a female, and then every time a female is coming, like 1, 2, 3, and 4. And so then they start to believe that it was in the wrong class, and actually it was true. And he creates this basing like of this series of probability and odds, and then look into that, you have this geometric sequence of logarithmic of odds. And yeah, I found, so here it's the sequence where every female arrive in the class. And you can see that there is like, you can describe this as a geometric sequence. So there is like a flow, I would say, of the data. And then based on that, you pass through you do like a linear function of the log, and you have the logistic regression. So it's very nice because I understood this all this process. And so here you have this representation. Or if you want to test if something is true or not, and you want to regress, do a regression with a continuous value, you have also here in this chapter how you can do it. And again, the difference in the Bayesian statistic is that you don't have just one value of each parameter that you want to assess, but you have again a distribution of these parameters, and then so also from in these cases you look to the distribution of what you want to estimate. And it's really nice because here there is both the implementation of a linear regression based like in the classical way, and or in the Bayesian perspective. So you have it both, so you can implement it both. Then in the last 3 chapters, you have a way to, because usually here we, in all the book, we work with the tables. So let's say a grid approach of to the Bayesian statistics. This is computationally feasible when you have 1, 2 parameters, 3 you can try, but when you have more than 4 variables, 4 parameters in your model, it's really difficult because you have to really make a grid to all the possibilities. And so it's like, it became like too expensive computationally. And so you can find some tricks to deal with that. One is the conjunct priors, where there is a mathematical bound between your prior distribution and your posterior distribution, your likelihood distributions. And so you can, to update the posterior, you can find some mathematical tricks to deal with all these distributions, and it's really nice. For example, if you have a prior distribution, this is a gamma function, it's linked to the Poisson process, or the uniform with the binomial, the multinomial with the Dirichlet distributions. They are all they are called the conjunct distributions, and so you have all these mathematical tricks that you can apply, but it's also limited to specific cases. Indeed, I would say that the most common is the Monte Carlo Markov chain implementation, where instead to have to test all the distributions, you do sampling of the distribution, so like an approximation of the final one. And so, for example, you pick like 500 of the events for each distributions randomly, and you assess in the prior, and you then assess, you work with that in the likelihood to assess the posterior. So you have a kind of approximation. You don't have all the possible values, and or it's they would say like a last attempt is the approximate Bayesian calculation, where you do simulations. So actually, it's like an approximation of the Bayesian framework, because you don't stick to priors and likelihoods, but just make simulations. And here again, all the examples. So I try to go through the books, because this is how I think it's a way to explain a little bit, but I don't know, maybe it was confusing or too many information, so boring, I don't know. So if you want to ask me something,
it was great to see how excited you were about it. Definitely the example with the bus and whether you should wait for the next bus or take a cab could be interesting.
Yeah, there are a lot of examples that you can really try in your real life, so it's useful.
Definitely. Are there any questions, guys? Yes, Michelle.
So I got 2 questions. My first question is, would you recommend this book to beginners, or do you think they need an a priori knowledge of how to code in Python?
So the Python examples, I think that are really basic. So are really pandas or NumPy function. Actually, they are not so complicated. Of course, if you already knew it before, it's easy for you to follow. But as it's when you deal with coding, usually you don't know everything. So every time you go there, and also for me, a lot of things were new. Also, I never used the data frame in this way, and so I'm familiar with coding, but also with Python. I started there are few months, so I was not an absolute beginner, so I had the basics of Python. And this book helped me to go further. And so, yes, I would recommend this book also to beginners, because it's not there are not like many things that are new or specific. Of course, if you know what is like a function, what is like if you have like I would say if you have like a basic knowledge in coding in general, it's okay, and then you can move to Python and try these examples, for example, and it's also a way to learn Python, I would say. Otherwise, if you never code in your life, of course, the impact is like, I think, a bit traumatic with, but it's also, you can also start with that. I think it's not impossible, and it's really feasible.
You had to.
So like my second question is, so we've seen the emergence of new software that allow to do Bayesian statistics. You got JASP, now SPSS, a new version. You got a Bayesian version of all the statistics that we used to do on matrices. But I still didn't see neuroimaging software that allow you to do Bayesian statistics beyond the fact that you test specific hypotheses with dynamic causal modeling. There is no software that is doing Bayesian statistics at the voxel level. Do you think it's because it's too time consuming in terms of computation, or do you think it's feasible and we'll see it happening in the future?
So actually, like in the background, several software use the kind of Bayesian approach. Let's say like ProbTract in FSL, when you have Markov chain to assess the parameters of the streamlines distributions, or Emeritrix for when you do like streamless propagations, you do Markov simulations on the fly. This is why it's like faster than ProbTract. So there are actually this approach already in the imaging softwares, but not if you were talking about like assess, for example, the like a regression voxel wise or these things. So yeah, I don't know if maybe it's feasible, because we are doing things that are also more complex. I don't think this is like impossible or computationally too expensive, but sometimes maybe we have to ask if it's worth it. So maybe we are happy with the, for example, in the regression examples, I was thinking, yes, it's really interesting that we can not have like just one value of your intercept or your like another model in the equation, another parameters in the equation. But then when you look at the distributions, it's really close. You have just a distribution of that value. So you are talking about an uncertainty. So I think that it's feasible. The thing is that we don't have these tools because they are too complex. So we are doing things that are more complex, I think. Also in the fMRI statistic, we are doing things that are more complex. I mean that if someone is interested in that, so if if we don't want just an R value, but a distribution of R values, to me, like in the regression, it's not like a big change, but it's really useful when you are comparing hypotheses. And so when you look to the posterior, and so not p-values, but the distribution of your hypotheses, to me, it's more interesting in this perspective. And so I wish that people will develop softwares also in the neuroimaging about that. For some other aspects, I don't see a big improvement, but maybe it's just me. I don't know, or like for me, it's really useful here when you want to test your hypotheses and or the odds against your hypotheses and another event. I find that really interesting. In other aspects, maybe I will be happy with the classical implementation, but maybe it's just me. This is my opinion.
Lovely, thank you. In the interest of time, I'm going to move us on because we have 2 more papers. Victor, do you want to go first?
Sure. Where is it? Here, I think. Yes. All right. So I chose this paper because I had heard about movie functional connectivity, which is basically some thing that have been happening for a few years. I think it's quite recent. Like I think it started in 2017. It aims to offer an alternative to resting state functional connectivity in a way that that gets people more focused on something, because as you know, resting state is basically a state of mind where you are where your thoughts are wandering around and you're not focusing on anything special. And in itself, it is a cognitive state that is interesting, but it also is something that might be a little variable between people, because they will not think about exactly the same thing. They will not have the same kind of focus during the task or absence of it. And also, it seems that the movie, watching a movie while doing the scan will improve the participant arousal, will reduce head motion, especially for children, which is a nice thing to have. And it also seems to have a test-to-test reliability that is higher for movie watching functional connectivity than for classical resting state. So it's a novel approach that is quite interesting, and that I had like very slightly heard of. It's not something that I'm really into, but that I thought it could be interesting. So when I saw the title of this article, I thought that it could be a good chance for me and for you to discover a bit of what it is, and to check out how is it as a field this kind of field is advancing. And so this comes to this article that is trying to see the consistency of the functional connectivity, but instead of having the consistency across different scans, MRI scans, but with the same movie, they try to see if it has the type of movie you're watching will change the functional connectivity patterns and the consistencies of different things that you can get with this study. So yeah, does movie watching change your functional connectivity if you change the movie, basically? And so this is a very good question, because when we do like group analysis or big cohort analysis or meta-analysis of different studies with resting state, we assume generally that it's the same thing because it's just resting state. But if you want to do the same thing with movie watching, if you don't know what the effect of different movies are, you need to have people watching exactly the same movie, which won't happen because different study will use different movies. So they try to see if the movie has any importance. So they use the HCP dataset that I just learned that they had movie watching fMRI in their dataset, so it's nice to know. So they try to see if they do several different tests to check if the reliability of the scans. So they do it both. So here, this is like some raw results that they acquired. It's functional connectivity matrices for different for the different runs. So they divided, so it's based on ROI functional connectivity. So they have a parcellation of the brain that they use to define the different areas that will correlate together, and they are subdivided into different networks. So as you can see here, you have the networks, and inside, if you look closely, you can see that there are different lines in each network that are the ROI. And they do also the analysis on a network-based connectivity, which is basically just the mean values inside of all the ROI in a network. So this is just the raw data. So there is when pulling all the movie together, this is the average matrix of connectivity. Here, the average matrix of connectivity, but for the average for the different networks, and the different movies connectivity matrices. And as you can see, it's at least as a first approximation, it looks the same, so it's great. So they used ICC, which is intra-class correlation, to estimate the variability of each connectivity point in the matrix, and it's they say that it's quite similar to the one that they get with the resting state, so that's nice. But so this is just the one basic first thing. What they did also was to try to see if they could do identification of individuals, so of participants using the matrices, to see if it was using, for example, let's get down. So they have 4 runs per participant because they had what was I saying? So they had 4 runs per participants. Not all participants watched the same movies, but I'm a bit confused. I don't remember exactly why, but anyway, sorry about that. So they try to identify participants based on their functional connectivity matrices by correlating the run of for the matrices of one run of participants with the matrices of a set of with the correlation. Sorry, by correlating the matrix of one run with all the matrices that are available, and to see if the correlation, the higher correlation, will give you one of the other run, if I understand correctly, of the same individual. Basically, it's not hard to. The thing is not hard, but I have trouble to explain it. Sorry, but well, let's get back to basics. It's just trying to identify the subject based on their functional connectivity matrix, and it works really well for this, and it's the same kind of identification values that you have with functional connectivity based on resting state data. So that's good also. What they tried to is to predict the sex and the grip strength based on functional connectivity from the movies, and the sex prediction using it was where was it? was a partial least square regression that they used, which usually works really well with this kind of data. Yeah, so it's a machine learning algorithm, quite simple and very powerful. And so yeah, they try to predict the sex and the grip strength, and it kind of work. It's as you can see, it's about 72%, 73% in general for the prediction of sex. And that's actually way lower than what you get with resting state functional connectivity. At least at first, it's just at first glance, this is what they get. But what they were interested in was, is it different between movies? Basically, can you predict the sex of the participant based on one movie more than on another? And they show that there is actually no difference when you check as within one movie. It's they have the same kind of prediction power than using one movie to predict the sex of participant watching another movie. So movie does not seems to, within movie or between movies, does not seem to have an impact here, which is nice to know. The movie type does change the prediction value though. So as you can see, for example, here, movie 1 will have a much higher value of prediction than movie 2 or movie 3. So the type of movie that you watch will have an impact, but it does not change the fact that you can use the prediction of one movie to predict to get the value of another movie. So this I skip, was not really interesting for me. And so yeah, so just to come back on the fact that they had low value on prediction for the sex and the grip strength, they assumed that maybe it was because of the way they processed the data. They defined the RRI rather than the bad value, rather than the fact that it was a movie functional connectivity. And so they tried to do exactly the same as they did, but using the resting state data from the HCP, and they actually get the same range of value of prediction that they get with the movie. So this is really the way they did it was not optimal to do the prediction, but it does not put into question the fact that movie watching can still be used for this kind of thing and is equivalent to resting state, at least for this. So in the end, it seems that movie watching is still something that has to be explored a little bit more before it can be generalized, especially since there are differences between movies, and that it might be also important to note that if you have movies with strong emotional values, it might change a lot of things. But still, with their results, they show that with the kind of movie that were shown in during the HCP data acquisition, it's still quite easy to. Well, no, it's not easy. I mean, it's still. I mean, the value that you get from one movie can be translated to another in some fashion, and it does not invalidate the fact that you have different movies that have that can be used to predict one or the other values, and identify the participant based on a different movie watching session. Shows that you could pool all different movies watching functional connectivity and still have good good predictions, even if they are different movies. So it's a good step forward in understanding better this kind of field, but it's still work in progress.
Lovely. Thank you, Victor. Very exciting paper. Are there questions? Oh, whoa. Okay. I didn't see who was first. Evie.
Yes, so thank you, Victor, for presenting this paper. I was wondering, looking at the paper, if they use kind of sliding window analysis of these.
I don't think so.
Because for me, it seems to be the way to go with this kind of stimuli, because they use movies, and so they could separate different states. But I didn't see that, so maybe I didn't see it. But
no, I don't think they used that. I think it would have made it much more complicated, because here they wanted to try to see if they could predict stuff, functional connectivity from one movie to the other, and if you start to separate different parts of the movie into different states of mind, I think it would make the problem way more complicated for their purpose, at least.
It depends, because based on that, you can separate the different states of the different movies, so you can have common grounds for different movies. So maybe it's a way to go also. So
yeah, okay. I see what. Okay, all right. I understand what you mean. But you'd need to classify the different state of mind in each movie before you can then compare with other movies, I guess. So yeah, I think it could be a good method, but still pretty much way more complicated than the approach that they used. And yeah, probably one of the things to explore next. Thank you.
Thank you very much, Valentina.
My question is on the type of movie that they selected. Did they select the movie according to common parameters or general cognitive function assessed? And what type of movies are we talking about?
So they have there are two types of movies. They are the movies that are from the how do they call that? It's common something. It's what is it? So there are Hollywood movies. It's not full movies, because it's clips of different movies that are shown, and they are. So if I remember correctly, there are Hollywood movies like Star Wars, stuff like that. There are small clips of those movies, and they are I need to find it.
I'm just sharing the link to the movie in the chat for everyone. You can have a look at them.
Okay, thanks. I don't.
Yeah, I mean, they're very long movies like Star Wars and
but
Ocean 11 is average. But
okay.
Yeah, so many contents, different contents.
It's many different contents.
Still, they don't find any differences according to the type of movie.
Well, they do find some differences, like for example, in the prediction here, like I said, it's a different type of movie will have different type of predictive strength, but still, it's when you average everything, it's like, for example, as you can see, like movie one. So if I remember correctly, on the row you have the movie used to for the training, and on the column the movie used for the prediction. And as you can see, when predicting with movie one, the prediction was pretty good. Then when predicting with movie two, it will be pretty bad. But if you look at the training, it will be actually kind of the same all the time. So this is why it averages out in the end, but still there are differences. So it's more complicated than what it looks, I think. It's not like you have different movie, you will have different state of mind, and you can differentiate things, and it will not be comparable. There is a lot of things that can be compared together, and yet it will still be, you will still have different functional connectivity with different movies.
But as you said, Victor, there's quite a few papers these days that look at the movies and how to analyze them. So there will be interesting things coming out, I think.
Yeah, sure.
Over time.
For sure.
Right. I think this is all we have time for today.
Oh, yes. Sorry, Michelle.
But at least you're over-prepared for next week already. Bless you. Yes, I'm very sorry. We have to push you to next week in the interest of time. But you can go first next week. Right.
I see that Hervé still has his hand raised. Is it normal?
No, I don't know how to unraise it.
I'm allergic to frustration. That's just, I sneeze when I'm frustrated.
Fine, you go first next week. No, I have to still. Right.
Too much pollen. Too much pollen.
Yeah, all the spring out there with
Oh
the
my
rain.
God, I'm dying. It's on live on YouTube. Now you know my weakness.
Right. Thank you very much for coming this morning. We shall see you next Monday for the amazing presentation of Michel Thibault-Deschatten of this paper that we don't know yet. Have an exciting week in science, and I'll see you next